some of the MPI stuff has evolved over time. Like we just had a chat about MPI correctness, but one of the major things that I ran into in terms of MPI was that I had type defs. So you just had templated MPI calls. So I wrote a wrapper to it so that I could just pass whatever, and then some size calculation. And then sometimes I was like, oh, the size blew up to more than, and then because I had complex types, you would convert it to bytes, so I could always send whatever's there. So you have maybe some unpacking of it, but then you could have sizes that were bigger than 10 billion. You're like, what are you trying to send 10 billion in once when something can't store the amount that you're trying to send? And it was a bit hard to figure out what the issue was. So that's why I was mentioning it'd be great to have things that just warn about possibilities of errors. All right, so now on my code, VELOCIraptor. So this is a analysis tool for cosmological simulations. And given the crowd, I thought I'd make sure that I introduce what I'm actually talking about, what the tool is doing. So I'll introduce numerical cosmology and structure finding, and then I'll talk about VELOCIraptor, and then it has both MPI and OpenMP. I'm working on the GPU, but I'm not going to talk about the OpenMP and GPU bits of the Raptor, right? So if we go to this, for the people who want to actually use the pointer, here, no, it should be here. Nope. Oh, there we are. Okay, cool. Laser pointer. All right, awesome. A common practice for studying the large-scale universe, how galaxies form, how you go from sort of maybe early universe to late universe, understanding the formation process of galaxies and stars is cosmological simulations, because it's very hard to create experiments of the entire universe, right? So we do numerical experimentation. And this is an example of a cosmological simulation where you've evolved some approximations of the physical laws of the universe from an early stage of the universe to the current day, over 13 billion years, and you get this web of structure. So here you're looking at scales, our galaxy. So for people who had a picture of the Gleam galaxy where they have the Milky Way galaxy in this sort of image is probably something about this size. So here, this object would be sort of a galaxy, a Milky Way size object. You're looking at obviously very coarse grained resolution of the universe, but you're looking at things where gravity dominates, where the forces of dark matter and dark energy really play, and that's kind of the thing you're looking into. Now, to run these simulations, you need lots of memory, and you typically need lots of numerical, like discrete elements. So you basically run either cells, so like a gridding mechanism, AMR, or you also do particle dynamics. And you're looking at really, I mean, the ideal thing people want to push to is sort of like the trillion particle scale is kind of like a good, awesome scale, and hundreds of billions of particles are the nominal scale that people really want to aim for. So then obviously it has to be MPI, because if you're going to store a particle that's meant to have mass, position, velocity, other quantities, you're looking at, and you typically want double precision for a bunch of this stuff, then you're looking at an individual element consuming maybe a few hundred bytes, and then you're multiplying it by 100 billion, and then there's extra overheads. So it's a large computational problem. And the analysis of this is also then a large computational problem. And the critical step for doing this the simulation is that this, so in this case, I've generated a density field. So it's a projected density field of the cosmological simulation, where in this case, the very, very dense bits are actually a slightly bright yellow. The empty bits are light gray, dark bits, darker gray. You really want to extract more than just some nice pictures. So that analysis process is usually involving identifying all the bits of the structure that the universe you care about, and then doing further analysis on them. So use identification of clusters, extraction of properties of clusters, extraction of the surrounding interplay of let's say, the cosmic web, on how that might influence the growth of the structure across cosmic time. And so then you need tens to hundreds of nodes on photonics, let's say, to run this type of simulation, and even the analysis of the simulation. So running the simulation isn't enough. And that was kind of in yesterday's talk where they were looking at computational fluid dynamics and then looking at the data processing. The data processing for image generation wasn't as memory heavy as the numerical analysis. But in this case, the processing of the data can be extraordinarily computationally intensive and is a very memory intensive process. And so VELOCIraptor is meant to identify these regions. This inset here is identification of halos of a given mass scale, where I've tried to highlight specific sort of mass scales, and the size of the object indicates something sort of about its mass and its formation history. And you're basically trying to map this density field to these objects that then contain many interesting properties that you're interested in, to looking to map this virtual universe to observations of the real universe. Now, On that note, VELOCiraptor is a phase-space multidimensional subhalo finder. So it's the idea of this clustering finder. It looks at the phase-space distribution of particles. It makes a bunch of assumptions, but it then is able to identify structures. Like in this case, this object here would be representative of some larger merging object. So there is an object that's identified in the density field that consists of a bunch of objects merging together, if you will, some higher density clusters that exist as subclusters. And you want to then decompose this and identify and process this information. It is uses C++17, mostly C++14, but I make use of a bit of C++17. It's MPI+OpenMP, CMake. It uses parallel I/O by HDF5, so it's meant to really scale as much as possible. The largest thing I think we ran on was 35,000 cores for a very large dark matter only simulation, so not that much physics, but we really want to have a large volume and lots of resolution, so it does scale pretty well. And the basic idea for VELOCiraptor is you give it some configuration, you give it some input, you then do this search of identifying field clusters and then substructure analysis and output. And each bit has different sort of nominal, optimal MPI and threading placement in terms of NUMA regions and nodes. So this is a bit of a challenge because in different parts of the section of the code, you would want stuff to be threads to be NUMA close, because you could make use of some cache coherency in the OpenMP threaded aspect, but other parts are like, they're completely independent thread blocks, so there's no cache coherency. They're not processing the same bits of data. Some MPI ranks you would want maybe on the same node to minimize communication because they're going to be physically talking to regions that are physically tied. And other bits you're like, well, it's fine. They're not going to talk that often, so who cares where they are, right? And this changes across the course of the tool. And in this case, you can also call this as a library embedded in a full simulation code. So the full simulation code halts, does the structure writing, puts out a bunch of data, then keeps running. So the same type of processes. We don't use MPI sessions in this context. It's directly integrated in. So you have the full MPI environment because you don't want to necessarily transfer the data. If you're transferring, 50 terabytes of data across the MPI network all the time you want to do some analysis, that would be very slow. So instead, you just make use of and rearrange data necessary for each bits of the code, optimal bits of the code. So on that note, so the MPI decomposition, I'm going to mention this as well, that if you don't run it, if you run it standalone, the input produced by cosmological codes can be any order of splitting. So they'll just write some files that could be one enormous gargantuan file, 17,000. And the idea here is the code is supposed to read this and that usually there is no information about the distribution of the files and how they might map to a nice distribution of input for processing. So you kind of have to keep looking at the file and going like, where is this all going to get sent? So the I/O could be quite intensive in this process with also lots of MPI. But the idea is in this case, the MPI input, VELOCiraptor doesn't care what the MPI decomposition was of the original code. It restructures it for its own, whatever the initialization was, and then reads all these files and basically asks where particles should be based on some MPI decomposition. The decomposition I use is a space filling curve. And the idea of space filling curves is quite useful to do decomposition. There is some assumption here about the space filling curve and MPI ranks, because of course, I'm assuming the space filling curve of neighboring ranks will also be spatially possibly close. But if I'm just given sort of an arbitrary set of ranks if Slurm decided I'm giving you an MPI column, but I'm going to put rank 1 on node 1 and rank 2 on node 17. It could do that, right? If I just add column order and then just rank order. So it could say, I'm going to give you some terribleness. I'm assuming that is still semi-logical, but I'm trying to work around that assumption. So, but then the idea is that this space filling curve will then try to minimize the surface contact of all these little cells. So it basically displays a mesh, uses that mesh to decompose the system. And then the MPI is really, the decomposition is to try to minimize the amount of communication that would occur in possibility of searching back and forth. And the idea of the clustering processes is obviously going to involve local searches. So there's lots of local searching happening. And so you kind of want to have clusters embedded within a bunch of cells. That's harder to do a priori. So there's usually some processing afterwards. The MPI, this is something as well. So communication is dominated by asynchronous point-to-point. I have threads that are reading input. The other threads could be waiting and doing nothing. And they just basically get sent receives. There's a lot of data being transmitted here, and the types are also changing all the time. So you have a particle type, but it has integers are usually associated for ID, or long integers associated ID. Positions are often doubles, but you can have long ints as positions because you basically use the position as an identifier for some hidden mesh that tells where the position is. So you can get super high resolution information that way. So I don't even know the types necessarily. When I'm reading, I'm kind of like on the fly going, that's okay. I've read the pressure. And in this case, this code has decided pressure is floats. And the code has been compiled so that I'm going to treat pressure as floats. I don't need the extra precision. So fine, I'm sending floats. The next thing read is like some measure of some shock value. Maybe it's the Mach number of a gas particle flying through. And you're like, that, okay, maybe it's a float. I don't need the double precision. So there's a lot of MPI happening here. And I try to do this decomposition to minimize the MPI and also chunk all the MPI. Because if you're reading 100 billion particles, and you have these vast chunks of data being sent in. So you can quite easily kind of flood with lots of MPI communication. So I try to make sure that I also send in chunks, and there's some attempt to try to aggregate stuff so that I don't blast everybody all at once, and I try to chunk up stuff so that neighbor ones communicate to nearby neighbors communicate more often, and read threads are dispersed with the assumption that there is some information in the I/O. So I'll go on to that as well. But this is the complexity of just reading the data that I've tried to deal with. The MPI communication and search. So the idea here is you're dominated by local searches. The MPI will search its own local domain, but then needs to link all the particles in that domain and then search neighboring domains. So every MPI rank knows the rough cell decomposition of every other MPI rank. It'll ask, well, I know that there's a mesh overlaid over the entire computational domain, and I know that cell belongs to rank 2 and 7. So I need to chat to 2 and 7 if I need to search that cell. And so then it tries to localize clusters because then you're going to do a lot of analysis on these particles. So it makes no sense to go back and forth because there's going to be tons of computation per cluster. So then it localizes. This is a challenge when you have clusters that are larger than the memory of a node, and there's like no nice solution. It's just gets slow because then it can't do the decomposition. It can't isolate the thing to a single node, and then every time you're computing a property, you have to go across nodes and get some values back, and it's just terrible. But I try to do my best to get around this, and usually the code tries to warn that there's a cluster that might not be able to fit on a node. If a cluster is split across nodes, it always goes to the rank that has the lowest essentially number of particles. So MPI load balancing. The Z curve also tries to load balance this, so the amount of the cells is actually not equal, right? It depends because it's a highly clustered input data set. So they each get different volumes of the data set, but they all get the same amount of particles. Then the idea is then you have lots of pair-to-pair communication. So this is one of the codes that's like an MPI rank doesn't know how many particles it can need from every other MPI rank. It knows roughly which ranks it needs to talk to, but you have to send this lots of point-to-point communication. It's all individualized messages, right? Particle 17 goes here. Particle 17 also goes to this rank, but also plus particle 23. So if you're sending all these little point-to-point communications, it's painful. There's not a nice aggregation process. But basically, I try to minimize it by essentially using com pairs. So I generate all the tasks, the communication pairs I'm going to go through, and then iterate through so that there's load balancing of the com pairs. And I basically try to say, okay, if 2 and 7 are going to communicate, and then I can definitely have 3 and 6 communicate at the same time. So I try to make that happen. And I would like to have this better so that there's also some aware of topology. So if ranks on the same node, everybody who's on the same node communicate first, and then everybody who's internode then start communicating. Or have some fraction dominated with intranode communication, and then go internode to minimize the load. Because this can it's not slow, but it obviously is a big bottleneck, and it's a challenging bottleneck. So for the MPIO, I mentioned this, there's some attempt to try to distribute read ranks. So if I'm reading a bunch of files, so in this case, like reading 5 files with 27 cores, if there are 5 things that are going to read, in this case, it's actually 1 file read by 5 different ranks. They try to split it up so that there is some attempt that this rank will have mostly internode communication with a large fraction of the node and split this balance up. So there's a lot of intranode communication, but not a lot of intranode communication. That's what I try to do. It's the same thing when writing. You try to aggregate stuff so that these guys are all meant to be having spatially close clusters, and they aggregate, and you try to minimize the number of ranks of a given file. So in this case, it's parallel. All these squares are writing to the same file. All the same colored squares are writing to the same file or same ranks. You try to minimize the number of splits that occur across nodes so that most of the AIO, that if there's an aggregation process and some communication, that it's intranode communication, not internode. And so that's a lot of the MPI that's happening under the hood for VELOCIraptor to make it run really smoothly and really scale well, because these are the big bottlenecks. They're really challenging if you still get stuff. You can get a cluster that is, as I said, can't fit across one single node of memory, and then things are very slow. So I'll go to future work, right? All of this decomposition in I/O and the load balancing and everything else still assumes that there's some sensible ordering to the default calm world rank. So if I grab the default calm world rank, I'm assuming that it goes 1, 2, 3, 4, 5, 6, etc. And that there's some sensibility for the thread affinity, that if I'm doing multiple threaded, let's say I do only 3 ranks, each thread gets 4 cores, so each MPI process gets 4 OpenMP. In principle, I would be getting this sort of decomposition as well for an OpenMP environment. But this also then has this MPI process. Well, it won't spawn here, so this would be stuck, right? So it would complain saying I've got some overloaded of subscription. It might not go threaded. It'll just have 1 core or 1 thread. And in this case, these threadings, you could have core affinity not bound to cores. So you can get core affinities that kind of go everywhere, given by Slurm sometimes, where this guy goes, there's the MPI process, but it has 4 MPI threads, but the core affinity is given the entire node. I've seen that weirdly happen. And same thing for this guy, so they can hit each other, which is terrible. But that definitely can happen. And so I still in VELOCIraptor making some assumptions that's always sensible, and I'm trying to work the stuff so that it actually checks that it's sensible. So then it checks the number regions and checks the thread affinity and core affinity, goes, this is not sensible. And I don't know if I should just reject it and say, hey, it's not sensible, or try to do something a bit more intuitive about reordering stuff. So I'm looking at trying to reorder the rank ordering that I get from the calm world to try to make this a little better, so that you maximize internode communication if you need it, and minimize the internode communication as much as possible, and also maximize thread locality as much as possible for the core affinity. So that's where I'm going to, which is basically going to use a bunch of stuff like NumaCTL, LSCPU hostname to get some information at the start point, and then try to come up with a better decomposition. So that's future work. I don't know many codes that actually do this type of stuff in production run. There's also usually assumptions of just like, you gave me an MPI calm world, and I'm assuming it's okay. I'm trying to work around this because there's funny things with like GPU affinity and so on that we've encountered. So just a refresher. The summary MPI code, the OpenMP code that finds structures in cosmological simulations. I'm going to add better OpenMP tasking, GPU parallelism, and MPI decomposition tied to NUMA topology, and then add some parallel I/O improvements as well. And with that, I will leave with any questions if there are any.
Thank you. Questions here from the audience online? Okay, if not, you mentioned topologies.
Yeah.
Have you looked at the rank reordering in MPI topologies? Is that something you can use?
Yes. So that's what as I said, because I've never really done it, but and for the most part for the earlier systems, it was not heterogeneous enough that I really cared.
Yeah.
But now I can see it if I really scale in some heterogeneous systems. So yeah, so that's what I'm going to try to do. And I was going to play with that, and then also play with my own, just to see what is easier to manage, because the biggest complication is that the amount of internode communication varies quite a bit as the code goes through different steps of the process. And it's not like and also the thread affinity, because it also uses OpenMP threads. So normally I would say this code should be always deployed as hybrid. Give a bunch of threads to an MPI process, not that many MPI processes per node, but you can go full MPI, and you can go, if you have a node big enough, full OpenMP. But the challenge is like, should I try to, I mean, it constructs tons of communicators on the fly as it goes along to different processes to kind of do some of this, but it's not ideal right now. And so, because it also still makes that general assumption topology. So it's the start point that I probably will look into.
I think Christoph would be the person to talk to if you want to have more input on that. Other questions? Yeah.
Thanks, Pascal. So, well, I probably not understood fully, but I guess the workload is very imbalanced. So some of the cores are doing a lot of work if they are close to a cluster and some are doing not
So
very much.
the initial decomposition, right? So let's say I start off and I try to load balance the number of particles that are there. That's just a memory load balancing. In terms of workload balancing, if you have lots of small clusters in this volume, so let's say the volume was split up so that it's really asymmetric. One rank has one cell because it's got, there's tons of particles in that one cell, and the other ones have all the other cells. That would memory balance the stuff, but in terms of work balance, identifying one large cluster and then all the subsequent substructures takes a lot of processing. But the amount of also, if you do have the sparse sampling where you have lots of small clusters, that also takes different types of lots of processing. So but the computational load is different. The big cluster will have certain aspects that are super computationally heavy. So the calculation here of the analysis, calculating the properties for the object. If you have a super large object, it tries to do the OpenMP threading on the object, not on like individual into objects getting a thread, but one object getting all the threads, sorry. And that can be quite this will have a couple of calculations that are very common, that are very computationally intensive. But there's only one. And so then once you're done, you're done. And the other ones might have many. So then there's also that caching. So here, everything would be one cluster would be also like, you would have some ordering so that there's a lot of cache coherency. You can use that to speed up the code. And the other ones, there's no cache coherency. There's just lots of little small clusters. So one thread gets one region, another gets another region. And they might step on each other's toes. There might be a couple that are close. And so then you get maybe less work, but there's no benefit of cache coherency. Like I can't make use of anything that would improve speed, like in terms of cache coherency. So it becomes a challenge. And there's not a trivial way, there's not an easy way of immediately determining workload balance and memory load balancing and I've tried to play around with this, but it's not that obvious. Because some of the things you have to iterate for. So if I'm looking at a blast, if I'm trying to identify a shock, I can identify a shock. But if I'm trying to calculate compression and also the origin of the shock, you have to iterate across the shape to figure out where it's coming from and then go, that's an iterative procedure. So it can take a while to figure out what I found.
Other questions? We still have 5 minutes. We just called it. I was actually wondering, you mentioned OpenMP multiple times, and I'm not quite sure I understood the challenges that you're facing in that combination.
So it's not in the combination. It's in the fact that for OpenMP, there's some portions of the code that it would be like a simple OpenMP for loop, and you can make use of cache coherency. Right? So you bits pull in memory, and so the threads can get that speed up. But there are other parts where there's no cache coherency. So it didn't, but there's a lot of memory movement. So then if I have all my threads on the same NUMA region, they're all sharing the same memory channel. In some cases, that's fine, because the bit that's pulled in by thread 1 is useful to thread 2. In other portions of the code, that memory bottleneck suddenly appears because it's not that type of calculation. Even if I'm trying to use task parallelism, you would rather have them sit on separate memory channels. And so then that reordering is challenging because you just have to take the hit to some extent, which one is the more dominant bit. And the a priori, I don't know if I read in some data, unless I characterize it, and I've tried to figure out some characterization so I could figure this out, but it's hard. I don't want that to be computationally intensive to say what would be the best core affinity for that code, for that input data that you're going to then process.